Okay, so I really wanted to make a video starting with section 312 because this is really when we get into working with our model kit. So when we talk about these cyclohexanes and how they have angle strain, what I want you to do is take some carbons and make a triangle with them. So you have your single bonds. Let's just use this one. Right, so you have 3 carbons here. And look when you actually make a triangle, how hard you have to force that together, right? You can actually see the angle strain that is being caused on this molecule. It's almost painful to look at. And just as a reminder that carbon makes 4 bonds, you can fill in the hydrogens here. But remember that an sp3 carbon has that 109.5 geometry, which is really its optimal geometry, and this isn't that at all. The internal angles of a triangle is what is 60, so we're almost less than half of the way there. So yeah, you have this angle strain. You could just see the pain in this molecule. So let's add and let's make it a square now. So go ahead and undo your triangle, and we'll add on a 4th carbon here. And you can see, all right, well, you know, the internal angles of a square are 90 degrees. So we're a little closer to 109.5, but still not quite there. And then we'll go ahead and we'll fill in our hydrogens. But you can still see, you can actually physically see the bend on those sigma bonds there. And you also don't see squares or triangles in organic chemistry anywhere, and this is kind of why. This is an unstable molecule. There's too much strain. But let's add a 5th carbon and see what happens. Because you do see pentagons. You see those in biology also, like a pentose, for example. So for a pentagon, I don't remember the exact geometry here. But let's see, internal angles of. Don't forget to fill in your hydrogens. So this is 108, which is just below 109.5. So here we have, this is cyclopentane that we just created. And yeah, it is. It's 108 degrees of the internal angles. And you can see that there's really not a lot of bend there in our sigma bonds. It just feels right. But the other thing that you can really clearly see with a pentane is that, you know, pick one carbon to be like the top, the point of this pentagon. And you can see that you can kind of bend it up a little bit pretty easily, so that the 4 carbons here are all in plane, kind of eclipsing each other. But this one's kind of at a head. And you can also bring it down. You can kind of see how the other carbons are going to kind of react. So you kind of have this, like, almost like you're kind of doing a sit-up a little bit. And that's going to be important in a second, okay? In the book they call it a pucker. One of those carbons here can kind of pucker out. Okay, but now let's talk about cyclohexane, because that's really the end-all be-all of organic chemistry. So go ahead and add your 6 carbon, because this is really where it starts to get interesting. So the internal angles of a hexagon are actually 120, which are more than that 109.5. And you can see that when we look at this, there's almost no strain at all. This is almost a perfect molecule because there's almost no strain at all on these sigma bonds here. Okay? But the other thing you can do here is you can not only pucker what's a point at the top, but you can also pucker at the bottom. And that is our chair. You can see that these four in the center, 1, 2, 3, 4, all can eclipse themselves, and you have this one pointing up, and you have this one pointing down. That's a chair conformation. And you really need to build this for the first time to see that these carbons, these 6 carbons, are not all planar. They're not all in the same plane. These 4 are, but the ones at either side are not. One puckers in and one puckers out. So that's a chair. Now, if you bring both to go up like this, that is a boat conformation that I just created here. I know it's hard to get this on camera. You can see the 4 kind of on the bottom there eclipse each other, but then you have 2 kind of going up. But the important thing about this, and this is where I really want to talk about the equatorial and the axial bonds. So build cyclohexane like this and kind of play around with it a little bit. But you can see that when you put it into a chair conformation, that 3 at the top, 3 hydrogens are going to be pointing right at you. So that's 1, 2, 3. And if I'm looking at the chair like this, they are going directly up. Those are the axial bonds. Those are the axial hydrogens. And if we flip this over, we can see that on every other carbon, we also have 3 hydrogens that are in this axial, kind of coming straight at you. So, flipping it around again, which is really the same thing, I have axial going up, axial going down, axial going up, axial going down, axial going up, axial going down. It goes every other. And you can see around this cyclohexane the equatorial bonds. So this one here, which is kind of the head of my chair, the carbon is puckered up. I have this axial hydrogen going up, and I have an equatorial hydrogen going down. Go to this next carbon here. Now I have an equatorial going up and an axial going down. So you can really clearly see what those equatorial bonds look like. They're angled down or they're angled up. Each carbon has an axial bond and an equatorial bond. And if one of those is going up, the other one has to go down. So this one here has an axial going up and an equatorial going down, an equatorial going up and an axial going down. Here's what I want you to do. Put this aside. Build this a second time so you get practice. However, make all of your axial bonds, pick a different color. Green, I think, technically is chlorine. It really doesn't matter. We can pretend that these are hydrogens. And I didn't realize this until studying this class for the second time, but this instantly makes it clear. Just look at the color green. Look at, as I'm holding this chair conformation, literally around the equator, you can very clearly see the equatorial bonds, and it's almost like a merry-go-round. It goes down, up, down, up, down, up. And you can very clearly see, almost like flagpoles, these white axial bonds at the top. It's really a beautiful thing if you really look at it. And, you can sort of like force your carbons to all be in a single plane here. It's not really ever how a cyclohexane looks. So to really make a chair, again, just pick 4 carbons that you're going to put on the same plane. Take a head and go up. Take the opposite. So this, I went up. This carbon, I'm going to go down. And then kind of take your 3 axial hydrogens and just make sure that they're all pointing like directly at you. And then go to the bottom and kind of finagle it the same way, and that's how you get kind of a perfect chair. Now here's the thing. If I flip this way, you know, this equatorial bond is going down, now this equatorial bond is going up. This is the same exact molecule. If I'm not adjusting or bending anything, I can rotate this way, pick it up, rotate it this way. It's the same molecule. That's something that you have to keep in mind. However, when you talk about a chair flip means this is the head of my chair going up, this is the head of my chair going down. What I'm going to do, and watch very closely, all the bonds here. I'm going to take the head of my chair here and I'm going to bring it down. So now I kind of have like this reverse boat type of thing. And now I'm going to take the foot of my chair and I'm going to go up. And I'm going to kind of straighten it out a little bit. And look what happens. Now look at what's in the equatorial position. It's all of the white atoms, the hydrogens. And now in my kind of flagstaff positions, I have the green ones. So a chair flip makes anything that was axial equatorial and makes anything equatorial axial. And it's really quite amazing. The other thing is, let's chair flip this again. Let's pay close attention to this atom here, which is going, this carbon here, which is going down. So if I do a chair flip, now this one has we'll call this hydrogen equatorial up and a chlorine axial down. However, if I do a chair flip, now that white hydrogen, it's still going up. However, now it's in the axial position. And the green is still going down, but now it's in the equatorial position. So that is how to build a cyclohexane and how to very easily find what is equatorial and what is axial.